Hi, this is a video podcast for Stage 2 Physical Chemistry at the University of Plymouth and is part of a series investigating the shapes of molecules and how this affects their spectroscopic behaviour. This podcast is devoted to the symmetry element called a mirror plane. Let's return to our hexagon with its imaginary numbers. Whereas previously we looked at how rotating the shape described its symmetry, the type of symmetry element we are going to look at now is called a mirror plane. There is a mirror plane possessed by this shape that runs through the vertices that are labelled as 1 and 4. This mirror plane swaps some of the labels over. The vertex labelled as 2 changes places with the one labelled 6, and the vertex labelled as 3 swaps position with the one labelled 5. Our labels are back to front, but don't forget that these labels are only there for our convenience, so that we can see the effect of the operation. We need a symbol to denote this symmetry element, and we use the Greek lowercase sigma. When we considered rotations in the previous podcast, the next thing we did was to look at the effect of repeating the symmetry operation. Let's look at what happens if we do a second reflection in the mirror plane. The labels return to their original positions. In other words, performing a reflection twice is denoted by our symbol E, the operation of do nothing. This is a general result. A mirror plane operation performed twice always results in returning everything to the initial position. Hence, from now on, we won't have to look for multiple symmetry operations from the mirror plane symmetry element, providing we remember that all shapes possess the symmetry element E. E, by the way, does have a name. It's called the identity element. There are two other mirror planes that are equivalent to this one. The first runs through the vertices 2 and 5, which swaps 3 with 1 and 4 with 6. The other runs through 3 and 6, which swaps 4 with 2 and 5 with 1. These mirror planes are equivalent to one another. We can only differentiate between them thanks to the labels that we have put onto our shape. We need a way of denoting three mirror planes that are identical. We do this by placing a full-sized 3 in front of our sigma. So far, so good. But this two-dimensional shape possesses more mirror planes. Whereas the planes we have seen so far pass through 2 of the vertices, these lie between the vertices. Here's the first one. This mirror plane swaps all 6 vertices. 1 and 6 swap, and so do 2 and 5 and 3 and 4. In a similar way to the previous set of planes, there are 3 of these. Make sure you can see how each of these affects our labels. This set of 3 is clearly different to our previous set. So to differentiate them, we add a prime after the symbol for this set of mirror planes. So far, so good. But all our work so far has been in 2 dimensions. As chemists, we are interested in real molecules, and even the most planar of molecules has depth, even if it's just the width of an atom. It's time to move into the 3rd dimension. Here's our hexagon in glorious 3D. This doesn't change the fact that we have a C6 symmetry element, along with C3 and C2 elements collinear with it, and two sets of three mirror planes. However, the third dimension does mean that we now have extra symmetry elements present. Firstly, we have another C2 axis running through the vertices we've labelled 1 and 4. This flips the hexagon over. Performing this operation twice gets us back to where we started, in other words, the identity element. There are two other C2 axes which work in the same way. One running through the vertices we've labelled 2 and 5, and another through 3 and 6. Just like the mirror planes, we notate this set of C2 axes as 3C2. And also, just like the mirror planes, there is a second set with the rotation axes running between the vertices. Again, we differentiate the two sets by adding a prime to the second set. Finally, there's an additional mirror plane that slices our hexagon in two in the plane of the hexagon itself. Now that we've got all three dimensions, we should also consider how these different dimensions are notated. By convention, the rotation axis with the highest order is called the principal axis, and this is taken as the direction of the z-axis and can also be called vertical. In our hexagon example, this is the C6 axis. The x-axis is defined as lying in the plane of the molecule, or the plane containing the most atoms. This leaves the y-axis, the direction of which is defined by the other two in the right-angled Cartesian system. If z is vertical, x and y are, of course, horizontal. We've now covered the most frequently encountered symmetry elements. Next time, we'll complete our look at all the possible symmetry elements by examining the less common ones.